The second speaker this morning is Magee from Durham University, and he's going to talk about optimal spectral gaps.
Okay, so I'm going to start with this statement that I have on the board. I'm going to explain it precisely. Where I'm going to arrive is spectral geometry in a broad sense, and particularly including arithmetic settings. So as most people here probably know, that is an area where Peter made decisive contributions throughout his career. From his thesis to his current program of prescribing the spectra of locally uniform geometries, which you can find online in his Turing lectures. If you haven't seen it, you should check it out. With many other insights and world records in between. As you'll see, my talk and my mathematics are highly influenced by Peter. Okay. So the way I want to begin my talk is, you can read this. Dan mentioned the result that almost every d-regular graph is almost Ramanujan. I want to begin by restating this precisely and also in a manner that will lead me to how to develop my talk. Okay. So when I do this, to make things clean, I'm going to make sure D is 2R. So I have even number of, even degree. Okay, so let me set some things up. So FR is the free group on our generators. Let's pull in X1 to XR. My talk is actually centered around representation theory. So let me tell you a special type of representation of a free group, finite dimensional representation of a free group. So I call this a type P representation. It's a composition of some phi n with the standard representation. I'll tell you what these are. I call this rho n. So phi n is a homomorphism from the free group on R generators to Sn. So after I've applied phi n to the free group, I'm in the permutation group Sn. Sn is a permutation group of n letters. And then I'm going to apply some irreducible representation of the permutation group Sn. So it's the first non-trivial irreducible representation. So the standard representation of the permutation group Sn maps from Sn to Un-1. It's the unique n-1 dimensional irreducible representation of Sn. Okay, well, that uniquely determines it, but let me tell you what it is. So you can view Sn as 0, 1 matrices, right? That is a representation of Sn, but it's not irreducible. It has two irreducible components. One is a trivial representation, one is n-1 dimensional representation. So this is what you get by taking the 0, 1 matrix representation of Sn and removing the vectors which are constant. Okay. Okay, so I care about finite dimensional representations of free groups and especially representations of this type. Okay, so how's this related to Friedman's theorem? Well, let me just say that if I do this, then rho n is in hom FR UN. So, nearly ready to restate Friedman's theorem. Right, so before I go on, let me point out that this set is finite because I have R generators and I have to say where they go in a finite group. Okay, so there are finitely many choices for the set. This is a finite set, and therefore it has a probability measure, the uniform one. So for fixed n, if I choose these guys uniformly at random, this gives me a homomorphism valued random variable. Okay, so let me now tell you what Friedman's theorem says in this language. So one way to say Friedman's theorem, if phi n is uniformly random, then with probability tending to 1, as n tends to infinity, which I'll henceforth refer to as asymptotically almost surely. Almost surely. You have the following. So if you take the following element of the group ring of the free group, x1 plus x1 inverse plus x2 plus x2 inverse up to xr plus xr inverse. Okay. Take this, this should be un minus 1. Take this representation, extend it linearly to the group ring, apply it to this element. Let's call it rho n. Okay. So this gives me a finite dimensional matrix. And then take its operator norm. It converges as n tend to infinity to the operator norm of something else, some other representation of the same elements. Okay. What is lambda? This should be lambda fr. Lambda fr is a left regular representation of the free group. So it exists for every discrete group, and it takes fr to the unitary operators on L2 of the free group itself. It's a left regular representation. Okay. And probably, what's that? Oh, I see. Let's put it up and then people can see. Okay, so you're probably thinking, what is this? Like, this is not what I saw before, right? What is this? It just so happens that we know how to compute this operator norm, and it's 2 root 2r minus 1. So why is this Friedman's theorem? Well, one way to get a 2r regular random graph is to pick r random permutations, or a homomorphism like this, and then form the Schreier graph formed by those r random permutations. And then this becomes the adjacency matrix of the random regular graph with the Perron-Frobenius vector removed. The model of random regular graph I used here is not the same as the one that Dan outlined, but it turns out to be the same to prove in both situations. Any questions so far? I did a data dump. Yeah.
Keeley graph, you mentioned the
No, Schreier graph, not the Keeley graph. So Sn acts on the numbers 1 to n. Okay, so I mean, I have an edge from I to j whenever one of my permutations maps I to j. The Keeley graph is a different story. Okay. So this is my starting point. Yeah, in general, this is not easy to compute, but in this case, you know what it is. Okay, this is what this number really is this thing. Any other questions?
On the bottom there, it says, so with what removed?
The Perron-Frobenius vector. So the vector that corresponds to the trivial eigenvalue, which is 2r in this case. The vector of all ones. Remember, I removed the vector, the constant vectors from my representation here. This removed the vector of all ones from the adjacent matrix. Any other questions? Okay, so this is fantastic. This is proved by Friedman. But if you want more, okay, you want more. So what more can you ask for? Okay. Well, you can ask that instead of having this asymptotically, you have it on the nose, or at least the upper bound. Okay. So what do I call it in my notes? Let's call this star. So how can we improve star? So the first one is the way that Dan talked about, which is to ask for an inequality less than or equal to with no limit. Yeah, I should make a remark that optimal.The tells us that the upper bound is the hard part. Maybe I should say it like this: the lim sup is the hard part. So instead of having a lim sup here, asking for a lim sup, you can ask for an inequality, no limit. Okay, this gives you Ramanujan graph. This leads to Ramanujan graphs. Okay, and as in Dan's talk, it's highly non-trivial that these guys exist, but they do, by Lebowski, Phillips, Sarnak, or Gulis. I'm assuming everyone here knows what LPS stands for, right? And the work of, okay, almost the work of Marcus Spielmann and Srivastava. Because they need to remove one extra eigenvalue, the one that comes from being bipartite. Okay. Well, I'm going to go on to something completely different, but before I do that, why not stop there? Why stop there? Why not ask for even more? So you could ask for, let's see, you could be very greedy and instead of say getting an inequality, you could ask for a strict inequality. Right? So you can ask for strict inequality, which is super Ramanujan graphs. Okay, and so it's, okay, I'm not going to say much about this, but there's recent work of Nina Zuberlina that establishes that there are infinitely many of these. And the work of Marcus Spielmann and Srivastava, again, almost establishes the existence of infinitely many of these up to the bipartite issue, right? Bipartite version. But this is subtle, okay? Even the existence of these guys is subtle. Okay, this is not the topic, I just wanted to mention it. Okay, so what I'm going to do is something completely different. Okay, so I definitely need to keep this. Okay, so everyone should remember that a type P representation is a representation that factors through a permutation group in this way. I know. I don't want to use the top words. Okay, so that's Ramanujan graphs. What else could you do? Well, you can look at this and look at this element of the group ring of the free group and say, instead of asking just for this guy, this linear polynomial in the generators, I could ask it for more elements of the group ring. And in fact, you could ask it for every element of the group ring. That's B. Ask star for every Z. I call this Z. And this Z. In the group ring of the free group. And that's what I'm going to talk about today. So I'm going to make a definition. Before I do that, we can be greedy again and say, why not both? Okay. Why do we not ask for an inequality? So, no limit inequality for every element of the group ring. That's not possible. Okay. So that's my remark. For the free groups that we're talking about now, both A and B are not possible. So here's my definition.
Like, was that sentence both A and B simultaneously not possible?
Yeah, does that make sense? Okay, thanks.
Simultaneous. Yeah. Simultaneous. Thank you. So I've already talked about free groups so far, but I want to make a definition which is very broad and applies to any locally compact group. And because I don't want to think about pathologies, I'll make sure it's Hausdorff as well. Every group I actually talk about will be simple to think about. So suppose that G is some kind of nice group. Let's actually just say nice. It's a nice group, locally compact Hausdorff. So if I have a sequence, rho I, which take G to the unitary operators on some Hilbert space, there are unitary representations. In this case, they were finite dimensional. I'll say that rho I converge strongly to the regular representation of G if for every F in C infinity, CCG, the limit as I tend to infinity, norm rho I of F is equal to the norm of lambda G of F. Where rho I of F is the integral rho I G d har, left har measure, times weighted by F of G. Okay, this is a definition. Okay, and I want to add a layer to that definition, which will allow me to talk about random representations. So this is a deterministic sequence of representations, but if I want them to be random variables, I can just ask that they're random variables. And then I could say that this holds asymptotically almost surely, or almost surely, if this limit holds asymptotically almost surely, or almost surely. Okay, so I just randomized the definition. Okay. Okay. So because we all know that the Ramanujan property is very strong. This is also a very strong property to ask for a sequence of finite dimensional unitary representations. It's actually so strong that it's very non-obvious that, okay, it was very non-obvious in the past that even for the free group that such a sequence of finite dimensional unitary representations even exist. Okay, so for any given locally compact group, if you ask for representations like this with some property, say finite dimensional, some other property that we'll see, it's highly non-obvious that they exist. So I want to make a further definition, which is just about the group. So if G is discrete, let's say, and there exists finite dimensional rho I that strongly converge to the regular representation, lambda G, then I have a name for this group. I say that G is purely matricial fields. And we're not going to worry about what this means. It comes from operator algebras, but we're going to call it PMF and just know exactly what it means. It means that there are finite dimensional unitary representations such that you have this convergence for every element of the group ring. So I did a lot of setup. Let me tell you some results and what this is used for. So it was an open problem for 25 years whether there exist finite dimensional unitary representations of the free group that converge strongly to the regular representation. It was solved by Hagerup and Thorbjornsen. This result says that the free group on R generators, say R's at least 2, is purely matricial field. It has enough finite dimensional unitary representations to converge in this way. So this result appeared in the Annals in 2005. What's important to note about this result is that it uses random matrix theory. In fact, every single example of finite dimensional unitary representations of the free group that converge in this way still use random matrix theory. And as a side effect, there are no known explicit examples. But I'm gonna tell you a candidate. Okay. So I think this is like the hot question in the field at the minute, to find an explicit example in an analogy with the Lebowski-Phillips-Sarnak Ramanujan graphs. Okay. So yeah, in the talk, there are going to be two main questions about convergence of unitary representations. The first question I'm about to state, it exists at the level of the discrete group. Okay. Let's state this. The question is, which groups are PMF? And you can also ask, which groups are PMF using type P representations like in Friedman? So I stated Hagerup Thorbjornsen that says that FR is PMF, but they use random matrix theory and they use GUE matrices, so they're using Gaussians. So they're definitely not using permutation matrices. So you can ask, is the free group PMF by type P representations, or can you actually extend this statement where you can replace this by any z, this exact statement, okay? So you're looking for this vast strengthening of Friedman's theorem, where you don't just have convergence of the norms of these representations that come from permutations on this linear polynomial, but on every polynomial.
So obvious that knowing this for this particular averaging operator doesn't imply this for every operator?
That's a good question. So like, I don't know how it could be obvious that something doesn't apply something, but I know what you're asking, and it's not clear what is the connection between being Ramanujan and having this strong convergence. There's possibly something there. Yeah. But I mean, this doesn't generate the whole C-star algebra. It generates the radial subalgebras. There could be some magic. I don't know. So that exact statement that I just alluded to, that was proved. So Bordenave Collins proved that Friedman's random representations converge strongly to the regular representation, asymptotically almost surely. It's kind of funny, like the reason this asymptotically is there is because of this thing that Dan mentioned, that there are these small graphs that cause you problems that you can't get rid of. Okay, and the corollary of this is that FR is PMF by type P. So again, it's a random matrix result, but it's random permutations. All right. So when I prepared my talk, I really hovered on the following conjecture. And so I thought a lot about it, and I want to be brave. But then I also thought Peter recently introduced the concept of theorem with a small t. So I may make it a conjecture. Yeah, I maybe make it a conjecture with a small c. So I'm a bit obsessed about this problem that there are no explicit examples. So I used my computer, and my computer convinced me that the following is true. So if you take SL2Z and you map it to SL2 FP, and then you map it to the unitary operators on L20, P1 of FP. It's not the free group, but it has a finite index free subgroup, and it will still strongly converge there if it's true. I predict that these converge strongly to the regular representation of SL2Z. So I'll be happy if someone can disprove this for me, and I won't have to think about it. As P tend to infinity.
Numerically, I think, well, Alice has checked.
Right, so the one, this was investigated, I'm not sure if it's people here, but this was investigated by Lafferty and Rockmore back in the 90s, I think. But they only went to P as 300, and I went to P as 20,000. And so they didn't go far enough to actually see anything happening. And I don't think they had this guess. So what they were checking was you can take an infinite I'm going off script now, but that's okay. Yeah. Ask me about this.
But you're specifically singling out this representation.
Because it's easy for me to but I don't think it's special. Okay, but this is what I got numerics for. This conjecture has some ramifications that I'll mention later in the talk, if it's true. So, like I said, I have one question which takes place at the level of discrete group, but I also have this analogous question which takes place at the level of a locally symmetric space. So this is question 2. This is supposed to be question 1. This is question 2. So now I'm talking about have in your mind SL3, SL3R, or SL2R, real semi-simple Lie group. For which G do there exist lattices? Gamma I in G. And you can enrich the question by putting any adjectives you want on the lattices. You could ask that they're non-uniform, uniform, arithmetic, congruence. For which G do there exist lattices, gamma I, with L20 G mod gamma I. So this is a unitary representation of G, converging strongly to L2G, the Planck's for L. This is the left regular representation of G. I just written it differently. Okay, so there are many variants of this question that are interesting. I think this question has not been asked before this, in this exact form before this talk. So, okay. Maybe I should keep this one.
Obviously PMF.
Well, there's some. Okay, yeah. So if you're not, there are some groups that have no finite dimensional like unitary representations. I mean, That's too obvious. For which groups is it not? Okay. So yeah, so the interesting ones are residually finite and finitely generated, I guess, to not have some silly things. I don't think it's really obvious for anything. Does anyone have an example?
Like amino groups, is there conjecture?
For Z, it's true. I mean, I haven't thought about general amenable groups, but we can talk about that. It's a different issue for amenable groups. Like the upper bound becomes easy and the lower bound becomes the hard one. So it's kind of a different story. Okay, so yeah, the most famous thing is like Selberg's conjecture. Selberg's eigenvalue conjecture. Implies that the answer is yes for congruence gamma I in, let's write it down here. Congruence gamma I in PSL2R. In fact, Selberg's eigenvalue conjecture is slightly stronger. It gives you the analog of having the strict inequality rather than the asymptotic inequality. But Selberg's eigenvalue conjecture applies this, but this is not known. Okay. Selberg's conjecture is not known. So what is this strong convergence really saying in this setting of lattices in PSL2R? So in this case, you can describe strong convergence. Let's call this dagger. Dagger is equivalent to the lambda 1 of H mod gamma I should tend to 1/4. But to go back, you should add that spec of H mod gamma I becomes dense in 1/4 infinity. And then there's something else funny that doesn't happen for free groups, which is to think this is discrete series. You should say that discrete series all appear. So if you work in this setting, you know that this is not hard and this is not hard, but this is the hard part. Just wanted to make it an if and only if. So this is quite general. I just didn't want to make a general statement of the spectral characterization of this strong convergence. I just wanted to do it in this example. There's something like this in general. This one. So my contribution is the following theorem, which is joint with my student, Will Hyde. Is yes to question 2 for following 2 types of lattices for either uniform, which means co-compact, and non-uniform. But in this case, you can add arithmetic. Lattices in PSL2R. So because of the spectral characterization of strong convergence, this implied a conjecture due to Boozer, that there exists closed hyperbolic surfaces with genus tending to infinity and lambda 1 tending to 1/4, which was not known before. So let me just say a few, this is the main theorem of the talk. So let me say a few ideas of the proof. We work with non-uniform lattices. The fundamental group is free, and hence it's PMF by the type P representations. So this is a crucial input that comes from Borden, Nav, and Collins. Then we have this input. What's that? Okay, we torsion free. Thank you. Okay, then we use resolvent methods. We use parametric construction of the resolvents using some random operators. And to get I'm just giving just saying the names of the ideas that appear in the proof. And then to get to this conjecture of Boozer, to get closed surfaces, we run some compactification procedure. So this compactification destroys arithmeticity, which is why for non-uniform we can put arithmeticity and for uniform we can't. Yeah, in the talk. Maybe I'll take a pause. Are there any questions?
So you do you have a number for what the lambda of SL2Z is? Like is that like that?
It's quite big, but it's bigger than 1/4. I can't remember the exact number. What's lambda 1 of SL? Does anyone know?
90 plus 90. But 91.
Okay, so this was the moment when we realized that like this property of being PMF or whatever was relevant to locally symmetric spaces. But since then, we got a bit more sophisticated. And so we understand what's going on better. So I wanted to explain that. Okay, so I wanted to explain very general facts. So I basically learned these facts in the seminar that Peter organized in the first term this year. I don't think I was completely aware of them before. So these are general facts that allow us to relate question 1 and question 2. So if you have a sequence of unitary representations, have rho I strongly converging to lambda gamma. The gamma is a lattice G. And you induce these representations, then you get strong convergence of the induced representations. Then the induced representation from gamma to G rho I strongly converge to, well, you can write it like this: the induced representation from gamma to G lambda gamma, but that's the same thing as the induced as just lambda G. That's the way things work. Okay, so this is about induced representations. Okay, what have induced representations got to do with surfaces with eigenvalues tending to 1/4. Okay, well, this is the first fact. The second fact is if the rho I are, let's just say they're exactly the composition of the standard representation of Sn and some phi I, where phi I is in Hom from gamma to Sn, then when you induce from gamma to G rho I, this is L2 of some covering space of G mod gamma. Except because standard removes the trivial representation, you have to say that it's L2, the new vectors in L2, of some covering space of G mod gamma coming from phi I. So this connects the induced representation to covering spaces, and this connects inducing representations to strong convergence. Okay? So I think what this means is, okay, it has to be co-compact. So in the case of co-compact lattices in G, this is very robust mechanism for moving strong convergence from the lattice to this locally symmetric space. So in some sense, what Hyde and I did was to get this to work in a non-uniform setting. Which involves dealing with cusps. So you have this robust mechanism, and to me that gives an impetus to try to provide new examples of representations of lattices in semi-simple Lie groups that strongly converge to the regular representation. I hope it's clear. Okay, I want to extend Booser's conjecture to other locally symmetric spaces as far as possible. Okay, but all is not perfect. So there are some obstructions. Okay, get rid of this. So obstructions. Yeah, please.
So this covering space, I guess, is of is degree n
Yeah.
and fold cover, and n will grow as I grows, or is that fixed?
Well, that is good. Okay.
Ni tend to infinity. Okay, in this convergence, Ni will tend to infinity. Okay, so here are two obstructions to like extending Booser's conjecture to all to everything. Okay, so the first one is that some lattices in real semi-simple Lie groups are known to not be PMF. Okay, the first one is that SL4Z is not PMF. SL3Z we don't know. Okay, that's an open question, guys. This is a result of mine joint with Mikhail Dedesal. And then there's an example that Peter told me that says that subgroups gamma I inside SL3Z cannot have L20 G mod gamma. You know what G is. G is SL3Z, SL3R. I'll write it. Converge strongly to L2G, where G is SL3R. And the reason is the existence of non-tempered Eisenstein series. You see that there are some subtleties to the theory. Okay. Yeah, so there are some non-tempered Eisenstein series that you can never get rid of in this, and they always cause a problem. By the way, there's no direct relationship between, or direct implication that I know of between like this setting and this setting. Okay, so these are two independent facts. It should be clarified. Okay. Okay, so that's the obstructions. Let's go back to proving things. So now that we know things work well for co-compact lattices, why not just prove Boozer's conjecture using the fundamental groups of closed hyperbolic surfaces straight away, and just going through this robust mechanism? Well, the point was at that moment in time, we didn't have the input. Okay. So for me, an orientable surface group is the fundamental group of a closed surface of genus at least 2, which is orientable. So we now know that surface groups are PMF by P. So this is a result of Lars Lauter, myself. This implies that there's an answer to question 2 for uniform arithmetic lattices in PSO2R. Yes, question 2 for uniform arithmetic lattices PSO2R. And in fact, there's a very, to say something about the proof of this, it uses the proof that surface groups are fully residually free, or in another language, limit groups. And so this proof actually does extend to all limit groups. So limit groups are PMF by P. So a group being fully residually free means for any finite subset of the group, you can map it to a free group and inject on that finite set. So you have many homomorphisms to free groups. But the surface groups doesn't really need anything fancy. But to extend to all limit groups, you need to use very strong results of Sella from his work on Tarski problem on the first order logic of free groups. Okay, so this uses Sella. Okay. So let's go back to my conjecture with a small c. What does that give? Okay. So the conjecture if you extend it to all non-trivial irreducible representations of families of irreducible representations of PSL2 FP, as Alex suggests, let's say we extend it. It would imply yes to question 2 for congruence lattices. Gamma in SL2Z, SL2R, I can say SL2Z, which is almost Selberg. What's that?
Some congruence lattices rather than all.
Yeah, I'm just doing primes, right? Yeah, if you have every irreducible representation of SL2FP covered, then you can take gamma P, like principal congruence subgroup gamma P. If you just take the Steinberg, the P1 of F, and you get some Nebentypus. Okay. Anyway, this is a reason possibly to put the small c, because this is really good. But I'm not saying I've almost proved Selberg. I just related the Selberg conjecture to something that lives at the level of the group SL2Z that might be very difficult to prove. Okay, so I'm not making any big claims here. I'm just saying there's some new perspective. I mean, maybe there's a proof of almost Selberg with analysis. Okay, so yeah.
Then it implies the strong convergence?
Yeah, that's more than strong convergence. So strong convergence says that you're like residually tempered. Like you may have some outliers, but in any compact part outside the Plancherel measure, that compact part eventually completely disappears. Right. So it's, yeah, so when I say almost Selberg, I mean Selberg, you're not getting lambda 1 at least 1/4, you're getting lambda 1 at least 1/4 minus small o of 1. In this hypothetical situation where this conjecture is true. Okay, I mean, but the strong convergence, okay, I don't know. It's true for, this works for random covers. Random covers.
You're not going to learn about all from random.
No randomization.
Your little C conjectures fail.
Right, the little C conjecture is what a deterministic, explicit sequence of representations.
All right.
Yeah, so let's just stick on hyperbolic surfaces for another minute. Eventually, we're going to go to hyperbolic manifolds, but first, let me say there's still open problems about, there are still fundamental open problems. I mean, even not assuming Selberg conjecture, there are fundamental open problems about eigenvalues of hyperbolic surfaces. You can ask if you can get lambda 1 to go to a quarter as the volume tend to infinity. You can also ask, okay, so these are open questions that someone should solve. So, okay, let's ask for Booser's conjecture. Do there exist xi closed hyperbolic surfaces with genus tending to infinity and lambda 1 of xi at least 1/4? So these are Selberg surfaces. Or lambda 1 greater than 1/4, which are super Selberg. What about if you don't care about 1/4? What about if you want to get some other limit point? So answering question of Peter, I proved that, let's make it a theorem. The limit points of the collection of lambda 1 of x, such that x is an arithmetic hyperbolic surface are all or equal to the whole interval 0, 1/4. So for every number between 0 and 1/4, you can find a sequence of hyperbolic surfaces with lambda 1 approaching that point, not equal to that point. Okay? That's what I'm saying. So obviously the hardest value is 1/4. Okay, that was my work with Hyde, but then the question is, how do you get everything in between? 0 is a result of Selberg and Randall. So yeah, there's still a lot to do there. So okay, I want to talk about one more result. Finish.
What is a Selberg surface?
That's exactly this.
Okay, is it lambda 1 is equal to 1/4?
At least 1/4.
At least 1/4.
Just being defined, just being said.
The Ramanujan graphs are named after Ramanujan-Peterson conjectures. And I think they should be named after Selbro conjecture. Yeah. Okay, so when you're, okay, these are questions about surfaces, but once you get done with hyperbolic surfaces and you go to hyperbolic three manifolds, and you try to say something. This is my ongoing work. So you can ask the analog of Booser's conjecture, but you should say that the volume tends to infinity instead of the genus. Does it open? Still open. Do there exist a sequence of hyperbolic three manifolds closed with volume tending to infinity and with lambda 1 converging to the optimal value, which is 1? Okay, this is open. Don't know this. But this framework of strong convergence and induced representations gives an avenue to try to attack that problem, right? Okay. So now I'm talking, this framework suggests to study hyperbolic three manifold groups and ask whether they are PMF, also PMF by type P representations. So we do have something here. Not exactly what I want, but. So this is joint work with my postdoc, Joe Thomas. So the master part of this theorem is that right-angled Artin groups are PMF. How much time have I got left? Because we didn't start.
You have 2.5 minutes.
2.5 minutes, okay. I'll be done. So what is a right-angled Artin group? It's something in between a free abelian group and a free group. It has some finite number of generators, and every pair of generators either commutes or not. And that's all the relations. Okay. Why do I care about right-angled Artin groups? They turn out to be some kind of universal group that many things virtually embed into. And being PMF is conserved under virtual embeddings. So this actually implies that by a very deep result of Egel and Wise, the hyperbolic three manifold groups are PMF too. This tells you that, okay, this is not what I want. I want covering spaces. I want actual locally symmetric spaces. But this gives me something. I only have unitary representations here. It tells me that every hyperbolic three manifold has a family EI over M, permission, finite dimensional, vector bundles, such that the first eigenvalue of that vector bundle tends to 1, which is the infimum of the spectrum of the Laplacian H3. Okay. Hopefully I've actually stated this right. And the dimension tend to infinity. So this is like some kind of strengthening of Egel-Wise theorem that the hyperbolic three manifold groups are virtually large. I'll stop here. Thanks for your attention.
Thank you very much for a beautiful talk. Are there any questions or comments?
Little c conjecture. That for every, what did you run out of?
We're on to Steinberg. S2FP to Steinberg.
Well, and
Which elements?
which element? Every element is good.
Yeah, for every element, there's convergence.
Which generators?
Interesting.
It's not true.
You can extract by subsequent arguments, some other feature element. Why?
I mean, you can.
It's an interesting question whether you could. It's quite a great thing to try to get something like the manager himself from almost from the common source.
People understood for a long time there's a connection between the spectral gap of the Cayley graph and the spectral gap, but this is you lose information if you just ask about the spectral gap of the rate.
If you put any element in the group, right, then it's a very strong statement. Yeah.
What is it? Could you remind me what it means to virtually embed a group gap?
It means just the finite index group that embeds. Okay.
Yeah, you have the statement about induction preserving strong convergence. Why does that fail for non-uniform lattices?
Basically, the elements of the group ring that you construct are not finitely supported. In the proof of this working, the elements of the group ring that you construct have tails.
Earlier, when you were talking about the numerics that made you believe this little C conjecture, you asked us to ask you some question, but I can't remember what that question was. But I'm asking you that question.
I'm not sure I remember either.
Why are you nervous about it?
I mean, I construct some operator that has no reason to be Ramanujan, but or converging to Ramanujan. But then I see it is converging to Ramanujan. I don't know why I'm nervous. It's just good.
It's something that you have to go further. Like so, Lafferty and Rockmore.
Lafferty and Rockmore.
They only looked
doing
at
random, and then there were counterexamples. And the question was whether they persist. Yeah.
But so there's this one way to test from. So you can take generators of SL2Z that don't generate SL2Z or even a finite index subgroup, and then just test the Hecke operator.
Interesting question.
Well, you mean SL2Z or PSL2Z?
You should be careful. Do I need to be careful about this? Yeah, I'm not being very careful on what I'm saying. We care about the free subgroup.
Any other questions or comments? If not, let's last time.